Hello, I'm I'm David. I'm coordinator of the Maths Learning Centre, and this is a revision seminar for Maths 1M. It's semester 2, 2021. If you're watching this online, hello from the past. I hope it's better there. And yeah, we're going to get on with it. So what we're going to do is we're going to have a look at my list of requests, and we're going to talk about them. And the rules are that you can interrupt me, and especially if I make like a maths error, like, you know, 1 + 1 = 1 or something like that, please let me know immediately. But otherwise, usually best to wait till I've got to the end of a sentence. But if I make a mistake like that, interrupt me immediately. So yeah, and I will attempt to remember to stop every 5 or 10 minutes and check in. Okay, so always okay to interrupt if there's something important that you want to ask. And if I say I'm about to say it, then that's fine too. Okay. Okay. Let me see if I can talk about this. So, excuse me. Right. So vectors have two lives. So from a physics point of view, a vector is a quantity with a magnitude and a direction. That's what it is in physics. And it's like forces and displacement, I think they call it in physics, and momentum, and you know, lots of things. Electrical field strength, and everything has magnitude and direction, and they tend to be represented with arrows. And there's a few little technical details about where the arrows are when you're doing forces and that sort of thing. But most of the time it works pretty well to think of vectors as journeys from one place to another. That's what vectors first sort of began as. Actually, that's not true. The concept of a vector started with Newton thinking about forces, but whatever. It works quite well to think of them as journeys. And then when you add two journeys together, you put the arrows head to tail, and that tells you the new journey. All right, over in maths, in a technical sense, a vector, a collection of things are called vectors if among the whole set you're allowed to do addition and scalar multiplication. So to a mathematician, a vector most of the time is just a list of coordinates. And depending on what you want to do with the coordinates, sometimes that list of coordinates represents a point, and sometimes it represents a journey. And you have to decide from context which one you're planning to use it for today. And it doesn't actually matter. Any expression, like algebra expression involving vectors, can be interpreted one way or the other when you need it to. But in general, it has to be a journey if you're adding or scalar multiplying. Okay. Might take me a while to just organize my thoughts on this. But in general, it's a list of coordinates. Now, you have seen this idea since you first learned about addition when you were like 8. Okay? So when you do, So just for numbers, when you do, say, 8 plus 5, right? You go, that's 8. And you run out of fingers when you add 5. So you think 8, and then you go 9, 10, 11, 12, 13. And so 8 is a place to start. And 5 is how far to go. And the answer is 13, which is a place you've finished. And on a number line, here's 8, and then you go plus 5, and then you arrive at 13. So ever since you learned the concept of counting on, where you have a number to start with, and then you say the numbers and keep track of how many you've done, ever since you learned to do that as a child, you already are treating numbers as sometimes places and sometimes journeys. And that's what we're going to do with vectors as well. How do you feel about that? Okay, cool. So if we're going to be here in two-dimensional space, and I have, and I'll do that in a second. If I had this thing, 2, like 3, 2 plus 1 minus 3, for example, then I could think of this as a place and this as a journey. 3, 2 is here, 1, 2, 3, 2 is here, and then I'll go a journey of 1 forward and 3 down. This is the place 3, 2, and this is the journey 1 minus 3, and we arrive at this location, which is 4, negative 1. Yeah, I could just as easily have written it in the opposite order and done this one as a place and this one as a journey if I wanted. Yeah. Now, some people, and you can also think of it as starting at 0 and doing this journey and then this journey and arriving at this place. So it is technically possible to do them all as journeys if you want, and saying, well, the journey of 3, 2, and then the journey of 1 minus 3 is the same as the journey of 4 minus 1. So you can think of them all as journeys if you want. So these are the two ways of thinking about it usually. There's location, and journey gives you new location. But you can also think of it as no matter where you start, if you go 3 this way, 2 this way, and then go 1 this way and 3 this way, then it's the same journey as going 4 this way and 1 this way. So you could also think of it as 3, 2 plus 1 minus 3 is 4 minus 1, and this is a journey. This is another journey, and this is the equivalent journey. They're the two ways of thinking about what vector addition is doing. I find this one easier to process. Place plus journey is new place, but this one is sometimes helpful too. And so just like fractions are capable of representing several different ideas, so are vectors. How do you feel? Okay. Cool. So that's the big idea I hold in my head to make sense of a lot of things. But you're going to need sometimes both of them. So now I'm going to talk about lines. So lines are a kind of set. They're a set of points. You know, you've got a line and it's got all these points on it. Infinitely many, usually. But that's what it is. It's a collection of points. You color all the points in and there you have a line. And so when I talk about any set of any kind, there are two ways to describe a set. One is to, I mean, there are technically three ways, but there are two main ways to describe a set. One is to describe how to make all the points in a set. With some technical details to make sure you do it right. And the other one is to say it's this type of thing. And here is a rule to decide if you're in or out. They're the two ways to build a set. Have you seen set notation with the curly brackets? So there are two ways to describe a set with the curly brackets. They look exactly the same in terms of their curly brackets and the such that sign. Some lecturers write this as a colon with two dots instead of a line. It could be two dots instead in that spot, but some people write as a vertical bar, just so you know. So this is read aloud as such that. And there are two ways to make a set. So for example, if I was in the plane, I could say the set of points with coordinates a and 3a minus 1, such that a is in R. So this is how to make the thing, and there's some technical details about what the letters in here mean. And this is a description of all of the points with coordinates that look like this. So I can come up with points on this line as long as I want. You know, if a is 1, I could have 1 and 3 times 1 minus 1, which is 2. And if a is 0, I could have 0 and 3 times 0 minus 1 is 1. And if a is 5, I could have 5 and 3 times 5 is 15 minus 1 is 14. And if a is minus 10, I would have minus 10 and 3 times minus 10 minus 1, which is minus 31. And I can just keep making new points in this set for as long as I like. But if I just had a random point, it would be not so easy to tell whether it was part of this set or not. So if I had a random point like 628, I'd go, oh, how do I tell? Well, I suppose if this is in there, then this a would have to be 6, and then it'd have 3 times 6 minus 1, which is not 28. Okay, so this is not part of this set, but it's hard to do. Okay. This set is aligned, by the way, just so you know. It's not the traditional way of creating a line, but it is a line. I know it's a line because 1, 2, 0, -1, 5, 14. They line up like that. If I'd done a equals 2, then I would have gotten 2 and 5, which would be about here. So yeah, it is definitely a straight line. I know this. Okay, an alternative way of creating a set would be to say it's the points x, y, such that y is equal to 3x minus 1. And this is what you're more used to with creating lines, is you have an equation like this. But any equation here would work as long as every point on the line satisfied it. So it could just as easily have been 3x minus y equals 1, and that would have worked as well. And this is a perfectly good thing that satisfies the rule. This is the kind of object we have, and this is the rule that has to satisfy to be on the line. So I can tell any point I think of, I can decide whether it's on the line by subbing it into 3x minus y and seeing if the answer comes out to be 1. And so I can see that, 628 is not in this set, since 3 times 6 minus 28 is not 1. Because it's like, oh, it's in minus 10, right? But say 1, 2 is on this line, is in the set, since 3 times 1 minus 2 is indeed 1. Yay. And that's the idea, the general idea behind making sets. And there are many, there are, useful ways to make sets and less useful ways to make sets. But this is the two ideas. So sometimes the equation you have here matches very neatly with how this is described. Because this is, look, this is the y coordinate and it is the x coordinate times 3 minus 1. Okay. Just want to, how are you feeling? But ultimately that geometry is about sets, and lines are sets of points, and some of them share points and some of them don't, and that sort of thing. Okay. So the classic way to make a line, so I believe in this course they have 3 equations for lines. And lines in 3D are similar to lines in 2D, but yeah, it's harder to make them in the same way. So it's mainly in 3D that they have the 3 equations for lines, isn't it? Yeah. So in all places, no matter how many dimensions you're in, there is one way that it's guaranteed to make a line. And a line can be thought of as having a starting place and a direction. So if I want to describe a line as a set, then I need to either have a rule for deciding if points are in the set, or I need to have a rule for creating all the points in the set, one or the other. So if I want to create all the points in the set, what I could do is I could think, well, if I start at this point and I go this far, then it'll be point plus journey equals new point. And that if that new point's on the line, then that's good. Then I've described the line very well. And I know that the journey to every other point on this line is in this same direction or the opposite direction, but either further or short, further or less far. And so I can think of a point plus some other journey, which is this journey. Let me just pick a journey. But it could be twice as far as that journey. And that means I go twice as far along the line. Or it could be only half as far as that journey. Or it could be minus that journey. And so it'll be plus some multiple of that journey. And this is a description of all the points on this line that we had before. So this is saying that I have the point 1, 2. And then I can go from that point any multiple of the journey 1, 3. So I could go 1, 3 and end up at this point, which is 2, 5. Or I could go half of 1, 3 and end up at this point. So this is 1, 2 plus 1 of the 1, 3. Or is this point here, which would be 1.5, 4.5. Is that right? No, not 4.5. 2.5. And that would be 1, 2 plus half of the journey 1, 3. Or I could go minus the journey 1, 3, which would be here, or 5 times the journey 1, 3 from there, which would be here. And every one of those journeys would land at a different point, and all those points would be on this line. How does that feel? Okay. And that works perfectly well in 3D as much as it does in 2D. So if I have a point, here in space, I could have, I'm going to wait till you finish writing that down. I have a point here in space, just there. And if I could go an arrow in this direction, that would get me this point. But if I went half of that, it would be this point. If I went minus that, it would be this point, and they would create a line in 3D space, which is easier to see if I did bring some stuff. So if I had like a point here and an arrow there, then if I went that way, then that'll make a new point just there. If I went 2 of that, that'll be a new point here, 3 of that, a new point here. Half of that would be a new point just there, minus that would be a new point here, and they would all join together to make this long straight line in 3D space. Whereas if I went that way, it would be going this way, and then that way, it would be going this way. So that is called the vector form of a line. And the vector they're referring to is the fact that I've written them as vectors, those points, the coordinates of those points. But even though it's called the vector form, the answer to this thing is always the coordinates of a point. And so what we have is that the points on the line that we have a place plus a journey gives a new point on the line. And if I choose all the different days of t, that'll be all the different points on the line that are produced. So this is the set notation version of the whole line. But ultimately, this is a description of what the coordinates of the points on the line are. Point plus journey. So that t is making the journey longer or shorter by multiplying it by 2 to make it twice as long, or half to make it, half as long. Or possibly flipping it over if it was minus. Cool. Do you have any questions? Is that adding anything to what you understand already?
No, it is. I think it's helpful to think that.
Yeah. All right, cool. So something to say about lines is that there are multiple different choices for how to create the same line. So given any line, there are lots of different ways to create the other points from a point and a journey. So I could create this line from this point and that journey, or I could create it from this point and that journey, and they would all produce the same line. And that's really important to know, that there are usually multiple answers to find a vector form for this line. There's not only one answer. So if this was the point P, and this was the point Q, and this was the direction V, and this was the direction U, then we would have that P plus TV, or Q plus like TU would both be possible versions for the line if you wanted. And these would both have coordinates, these things. So it would be like, let me just do a proper example. So if I had a line that joined the points 1, 2, 5, and 0, 8, minus 1, then it could be, there's lots of choices for how I could create the vector version of that line. I know that any 2 points do make a straight line, but all I need to create the vector form is a starting point and a journey. And so I know that the journey from this point to this point, I shall call this P and this Q. The journey from P to Q is the end minus the beginning. And the reason I know that is that end plus journey, no, so beginning plus journey, I'm going to write that down up here just a second. Start plus journey equals end. Therefore, journey must be end minus start using algebra, basically. So I can make the vector PQ, and now I could say that starting at the point P, so the vector form of line, the points on the line are the starting point 1, 2, 5 plus some multiple of the journey minus 1, 6, minus 6. That is a perfectly good version of this line. But I could just as easily have started at point Q, and that would have been fine too. That would have been just as good. Even though this arrow doesn't actually start from Q, if I did go that journey from Q, I would still be making more points on the line, and so that's okay. Traditionally, you do this direction, but it doesn't really matter. Or I could just do any point, like I could just do 1, 2, 5, and t of minus 2, 12, minus 12. That would also work too. Any multiple of this is fine, because it's still a journey that lives on the line. I wouldn't normally do that, but it's possible. You can do whatever you wanted. Any multiple of this is fine. So if you figure out a journey and it comes out to like 50, 20, 30, I'd use 5, 2, 3. Because that's easier. Because any multiple would be fine, because any journey that's in the direction of the line is fine. And you'll still be able to get to the rest of the line. You'll just have to have a bigger multiple of it to get further away. Cool. So that's great. That's a very vector way of thinking about lines. But the alternative way of thinking about lines is to say, well, they're just a set of points. And if I had a rule which I could sub the coordinates of those points into, and if it satisfied the rule, then it would be on the line. If I had a rule like that, that would be a perfectly good description of the line too. Because sometimes you don't want to create the points on the line. You want to take a random point and decide if it's on the line. And what you'd like is something to sub it into, where say if it comes out to 0 or whatever, then it's on the line. And if it doesn't come out to 0, then it's not. Something like that. That's what we want to create. And so when we talk about the Cartesian form of a line, that's what we're doing. We're creating that rule that tells you whether you're on the line or not based on a calculation involving the coordinates. So it's a rule you can sub the coordinates into to tell whether a point is on the line or not. Okay. So, yeah. So that's why the y equals 3x plus 1 or 3x minus 1 is a perfectly good Cartesian form for a line in 2D. In 3D, you'll need 2 equations for a Cartesian form, which is why it has 2 equal signs in it when you do it. Yeah, so in 2D, we need 1 equation. In 3D, you'll need 2 equations to make a line. Yeah. So I'm just going to write one down. It doesn't look like it is, but it's a perfectly good Cartesian form of a line. It's not what your lecturer expects, but I just want to show you what's possible. So for example, in 3D, the set of, no, I'm going to write the full set version. Set of x, y, z such that x is equal to 2y minus z and z plus y equals 3. These 2 equations describe a line together. It doesn't look like the Cartesian form of a line normally looks like in this course. And I'll say that any 2 equations, as long as they're not multiples of each other, that are like, they don't have squares or anything like that, should tell you where a line is. This is a line 2. But it's much more common to have something that looks more like, 3x equals y on 2, and in combination y on 2 is equal to z plus 5 or something like that. That's what you're more familiar with for a Cartesian form, I think, in Maths 1M. Is that right? But this is still 2 equations, and it's normally written like this. 3x equals y on 2 equals z plus something like that. It's normally written like this. But that's really 2 equations. There's one here and there's one here. So yeah, you need 2 equations to tell you where a line is. And this doesn't tell you where the line is. It just allows you to decide whether points are on the line or not. So I'm just going to write that down. So if I had a line, with Cartesian equations, 3x equals y on 2 equals z plus 5, then this doesn't tell me what any of the points on the line actually are. It just tells me how to decide if a point is on the line. And so I could go 0.158. Let's see, 3 times 1 is 3. That's the 3x. And y divided by 2 is 2.5. All right, so they're not equal. So these 2 aren't equal, so this point is not on the line. So 3x is not equal to y on 2, so this is not on the line. But if I had 168, then 3 times 1 would be 3, and 6 divided by 2 would also be 3. And so yes, this one's working. The 3x is indeed y on 2. That's good. Let's just have a look. The z plus 5, 8 plus 5 is 13, which is not 3, and so it's still not on the line because it's supposed to be the same as y on 2. Okay, so not on the line. It has to satisfy them simultaneously. So I'm thinking that it would have to be like -2, I reckon, if it starts with 1 and 6. So the 3 times 1 is 3, and the 6 divided by 2 is 3, and the -2 plus 5 is also 3. Yes, all 3 of those calculations are the same. It is on the line. Whoop. Yeah. That's what the Cartesian equations are doing. They're giving you a way of deciding if a point is on the line or not. But what they don't do is tell you any of the points on the line. And so that's why the vector form and the Cartesian form are both useful for different reasons. The vector form, it's really difficult to decide if a point is actually on the line or not from that information. And so it would be nice to be able to convert between the 2 forms. I believe in Maths 1M there's a 3rd form called the parametric form. It's not really all that different from the vector form. So it's just the vector form focusing on each coordinate one at a time. So let me just have a look at that other line I made. 1, 2, 5 plus t times -1, 6, -6. That's the same as saying 1, 2, 5 plus -t, 6t minus 6t. Because that's how vector multiplication works with coordinates. You just times this number by all of those numbers. And then you can add the matching coordinates. That's 1 minus t, 2 plus 6t, 5 minus 6t. And this is the parametric form. Like technically it's like the x coordinate is 1 minus t, and the y coordinate is 2 plus 6t, and the z coordinate is 5 minus 6t. It's called parametric because there is a single parameter that describes what the coordinates are. This letter t is called a parameter. If you do any statistics courses, they talk about parameters like the mean and the population mean and the sample standard and the population standard deviation. It's the same idea as just an unknown number. So the parametric form and the vector form are telling you the same sort of information. They're telling you how to create the coordinates of your points on the line. It's just that the parametric form literally tells you each coordinate separately, whereas the vector form tells you how to create the coordinates as a whole. Yeah. You okay with that? So the question is, how would I convert this to a Cartesian form so that I could tell whether a point is on the line or not? And starting from vector form, the quickest way to get there is via parametric form. Because the Cartesian form has an x and a y and a z in it. And so I've created a thing that says what the x, y, and z coordinates are. Now I need to figure out relationships between the x and the y and the z coordinates. So there are many ways to do this. One would be to rearrange this to see what t is equal to and sub that in, and then you have an equation involving y and x and another equation involving z and x, and that would be a Cartesian form for the line. But it's not what your lecturers are expecting you to do. What they're expecting you to do is to rearrange these so that they're all equal to t. So if I take the first one, I'll have t, if x equals 1 minus t, then I can move the t over here and the x over here and have t is 1 minus x. Like the second one, I've got 6 plus 2 plus 6t. So I'll subtract the 2 and divide by the 6. And then I'll also, if I've got the z equals 5 minus 6t, then I can maybe put the 6t equals 5 minus z and then divide by the 6. It doesn't really matter how you go about it. Now I know that whatever this parameter t is, for a specific point that is on the line, I can figure out what the t is by doing 1 minus x. I can figure out what the t is by doing y minus 2 over 6. I can figure out what the t is by doing 5 minus z over 6. And so that means that 1 minus x must be the same answer as y minus 2 over 6 because they're both equal to t. This is equal to t and this is equal to t, so they must be equal to each other. And in fact, it's also equal to this because this is equal to t. And that neatly creates two equations, technically three, but you know that this is equal to t as well, so it must be equal to this is equal to t and this is equal to t, so they must be equal to each other. And that is now a Cartesian form of the line. That's how to convert from vector form to Cartesian form. Go via the parametric form. You right? So yeah, it's very clever actually, that particular method. But ultimately, if I wanted to use this form to check whether a point was on the line, I would sub the x here and the y here and the z here, and they all came out to the same answer, then that point's on the line. If they don't come out to the same answer, then that point's not on the line. Which is the whole purpose of a Cartesian form, is for checking if things are on there or not. If you start with this, then you can do this process backwards. You can say, well, let's make them all equal to t. Since they're all equal to each other, they must equal to be some plain number. We'll call that t. Rearrange to get a formula for x, y, and z. That'll give you this. Then split those vectors up into a vector with the plain numbers and a vector with the t's. So that process works perfectly well in reverse as well. So that's nice. Do you want to see that done in reverse? Okay. So that's cool. That's how the three versions of a line are connected to each other. In a technical sense, this isn't an equation because it doesn't have an equal sign like that, the vector form, which is why I like to call it the vector form rather than the vector equation. But some people are a bit sloppy about that. If you want it to be an equation, you write equals x, y, z. Cool, that's lines, which is nice. I don't know if you've seen this in your course, but back here when I did this, when I do this thing and I do the journey from PQ, the journey from P to Q is this. And then I do that the points on the line points are 1, 2, 5 plus t lots of -1, 6, -6. This gives you all the points on the line. It gives you these points and these points and these points. It gives you every point. If you choose different values of t, you'll get different places. This t is sort of like a percentage of this arrow. Like 1 t would get you from P to Q. And then 2t would be twice as far from P as Q is, and so it would be over this side. And 1.1t would be here, and half of t would be here, and 2/3 of t would be here, and 0.1 of t would be here, and minus t would be this way. So if you just want to create a bit between P and Q, then you would choose the t to be somewhere between 0 and 1. Which is really kind of nice. It's like, well, we'll just go 10% of the way from P to Q and make the t 0.1, and 50% of the way from 0 to Q to make the t 0.5, and that will just fill in just a bit in between if you only choose your t's between 0 and 1. It's really cool. And that's part of the same idea that goes with curves, where you've got a parameter like t that tells you where you're up to on the curve. And this is a curve sort of version of how a line works. Yeah. Might close that door. All right. Okay. I always thought that was fun. Like it. So they reuse that concept in Maths 1A when they do convex sets. So, yeah. Okay. So that's pretty much all there is to lines, but there's some really classic problems that are all line-based that can be quite complicated. So that's lovely. If I am thinking of vectors as directions, then those directions can have angles between them. And there's a calculation you can do to figure out the angle between two vectors. So if I am thinking about two lines, they can have an angle between them. I mean, technically two lines have two angles. There's one here and one here. But this one's the same as that one, and this one's the same as that one. And it would be really nice to have a way of dealing with vectors to figure out what those angles might be. I know that given any line, I can pick an arrow on this one to describe its direction and an arrow on this one to describe its direction, and I've used them to make the vector form of the line. It should be possible from those directions to figure out the angle between them, and it is. It goes like this. So the angle between the vectors v and u, it's traditional to call them small bold letters, and I've underlined them so that because I can't draw bold on my paper. When you're thinking of them as arrows, it's traditional to do them that way, and when you think of them as points, it's like just capital P. So the angle between two vectors, let's just call it, if the angle between the two vectors is theta, then cos theta is the dot product of the vectors divided by their two lengths. Does your lecturer use a double line for length, like double lines? Yeah. And that's lovely. That's very nice. It relates trigonometry to dot products. And so you can define the dot product this way if you desire, but most people define the dot product as multiplying the matching coordinates and adding them up. So if I wanted the angle between 1, 0, 3 and -1, -2, 7, They don't have to be whole numbers, so let me just put a half in there. Let's do it. If I wanted the angle between those two, then I would first find the dot product. And that would be the 1 times the minus 1, and the 0 times the minus 2, and the 3 times the half. That's how you do a dot product. So do those 3 multiplications and you add them up. So this is minus 1 plus 3 over 2. And 3 over 2 is 1 and a half. So if you take 1, you'll get a half. That's the dot product. But then I'll also need the lengths of those vectors. So the length of 103 is the square root of 1 squared plus 0 squared plus 3 squared, which is the square root of 10. Not pretty. And the length of this vector would be the square root of minus 1 squared plus minus 2 squared plus a half squared. Oh man. That's 1, that's 4, so up to 5, 5 and a quarter. Oh, cool, look. Yay. 5 and a quarter is 9 quarters. Isn't it? No, it's not. That's 2 and a quarter. Damn it. So 5 and a quarter. And mathematicians prefer vulgar fractions, so 21 over 4, which is, there you go, not pretty. And so therefore the angle, if theta is the angle, then cos of theta is going to be the dot product divided by the 2 lengths, which is where I would use a calculator to help me. If I could find one. I'm sure in your exam you're not allowed to use Desmos on your phone, but this is what I've got. So a half divided by the square root of 10 times the square root of 21 over 4. And then theta would be inverse cos of that. So arc cos is what they call it in Maths 1M, but I will do cos inverse of the answer. 86 degrees. Oh, they want them in radians, don't they? 1.502 radians. Yay. Okay. I mean, which is about 86 degrees, but they prefer it in radians in Maths 1M, I'm pretty sure. If you write a number down and don't say whether it's radians or degrees, they're going to assume you mean radians. So just, if it's okay to, I don't know if it's okay to put degrees, but if it is in degrees, make sure you put the degree symbol. Just for completeness' sake, I'm just going to write that down. Three decimal places. Okay, that's how to find the angle between things, and it's very clever. It involves drawing some triangles with your vectors. Yes. Okay, cool. So you may notice here that you have actually u divided by its length and v divided by its length. That idea of dividing a vector by its length is really rather important, and it turns a vector into a vector that's in the same direction but has length 1. And that's called making a unit vector. And so it turns out that if you've got unit vectors that are already length 1, then the angle between them is just their dot product. So if the length of a vector is 1, then it's called a unit vector. And if you've got two unit vectors, then the angle between them is just their dot product, which is kind of cool. Which is kind of cool, really. And cool. So I'm just going to draw a picture. This is the vector u, and this is the vector v as arrows. I'm doing them as arrows at the moment because I can't really talk about angle between them if they're not arrows. Then watch this. Cos of this angle is that length divided by this length. No, this length here divided by that length. So this length here, which is the adjacent side, and this length here, which is the hypotenuse. So this is the adjacent. And this length here, which is the length of v, that's the hypotenuse. So cos of theta will be the adjacent side divided by the hypotenuse, right? But I know that cos of theta is also, based on what we learned earlier, u dot v divided by the length of u times the length of v. That's what I had earlier, which means that this here must be the adjacent side to the angle. That calculation there, that's called the project, and that is the length of the projection. So this action here of taking v and creating a triangle along the other vector, this is called the projection of v onto u. And its length is this bit, because it is the adjacent side of that triangle. And we're nearly there. So this is how long this vector is. It's in the direction of u. So if I made a unit vector in the direction of u, which would be a vector that's length 1, and then multiplied it by this length, then it would be the correct length. And so what you end up with is that when you project v onto u, you get that. Technically, you're doing this actually. Yeah, anyway, I'm just going to leave it like this. U dot v over the length of u squared times u. That is what you get as a vector when you project v onto u. I'm just going to draw the picture. Here's u, here's v, and this down here as a right angle. This is the answer to this. It is a multiple of u because it's pointing the same direction that u is pointing, possibly the opposite direction that u is pointing. And the correct number to multiply u by to get the right length is u dot v divided by the length of u squared. Now, you said before you weren't sure what projection was doing. How are you feeling now?
Yeah, a lot better.
I just have a couple of extra things to tell you. If u is already a unit vector, then this bit is 1. because the length of u is 1. So it turns out that if u is a unit vector, then u dot v is the length of the projection of v onto u. Is there a symbol for this? Do they write this as like proj uv? No? Okay, all right. So they just use words? Okay. That's a Maths 1B notation. Okay. So if u is a unit vector, then the projection of v onto u is just u dot v times u. Because the length of u is 1, so when you divide by it, it doesn't do anything. Which is really kind of cool. I like that. And that's why people care so much about unit vectors, because it makes all our other calculations easier. Yeah, so it is technically possible to project onto a plane and not just onto a line, which is what we're doing there. But I don't think you do that in Maths 1M. But basically, for a plane, you need 2 vectors to tell you what direction it's in. You know, one this way and one that way, and you'll just project onto both of them and add them up. So it's pretty cool. Only works if these two are at right angles to each other. So that's pretty much how it's done. And that's in Maths 1B as well. So lots of stuff in Maths 1M is there to set up for the later maths courses, but some of it's set up there to set up for physics and various other things. Yeah, so that's basically what projection is about. Like, so when you say the projection, you're creating a new vector. So the answer, so this answer is a vector. And we're living on the line that u creates, and so therefore it has to be a multiple of u, and this is the multiple of u that it is. That's what we multiply by u by to get the correct length for that vector. All right. I'm going to talk about, there's one more thing, which is the concept of orthogonal or perpendicular. That's in this course, isn't it? Do they use the word orthogonal? So orthogonal just means at right angles. And just so you know, it literally means at right angles. Ortho means correct, such as an orthodontist is a person who makes your teeth correct. And gon is from like polygon, it means angle. And so we have correct angle, right angle. Literally means right angle. So I just think that's cool. So it means at right angles. And the angle between them is 90 degrees. Cos of 90 degrees is 0. And so to tell if vectors are orthogonal, well, let's just call them u and v. You need find the dot product. If that dot product is 0, then they're orthogonal. But if the dot product is not 0, then they're not orthogonal. Yay. And so you don't have to worry about cos thetas or any of that stuff. Like a lot of people, when someone asks them in an exam about, you know, what's the rule for telling if things are orthogonal, they go, well, cos theta is equal to this, and then, you know, if theta is 9 degrees and that's 0, but you're allowed to just say the dot product 0 makes them orthogonal. You don't have to do all that cos theta stuff. You can just start with that. And that's because in other areas of maths where angles are a little bit hard to define, you can still define things being at right angles by using dot products and zeros and stuff without defining angle, which is kind of cool. Yeah, so that's just one of those things. And so you can run geometry quite well without angle, but just with the idea of being orthogonal. And so It's a strange world, but most of the time you don't really care. You don't really care about the angle, you just care about whether it's a right angle or not. Because if they are orthogonal, then all this other cool stuff happens. For example, if two vectors are orthogonal, then when you project one onto the other, you get nothing. So if you've got two vectors like this, you go the projection of V onto U is just going to be the zero vector, because when I come down here at right angles, I just end up there. Come all the way down here at right angles, there it is, because they're already at right angles. Yeah, so that'll happen, but also because the dot product is zero, the correct length for this vector is u dot v divided by the length of u, but u dot v is zero, and so the correct length is zero, and so you just get the zero vector. So that's something that orthogonal vectors do. Yeah, which is nice. And the dot product has all these properties about how it expands out over addition and scalar multiplication, and that makes it useful to do proofs involving dot products when you're interested in things being at right angles or not. So one way of doing geometry proofs that are about right angles is to turn everything into vectors and use dot products to help you. I can't think of a good example now, but there were some extremely frustrating vector proofs in Maths 1M assignments traditionally. And any time where they talk about something being at right angles, that's telling you that you need to do dot products because some of them are going to be zero. So as a thing to do to vectors, dot products is a good one. Like you chuck vectors in, it spits a number out. And sometimes that number is zero, and if it is zero, then they're at right angles. There's not much more to it than that. Yeah. I can't think of any good examples of using it in a proof at the moment, so I'm just going to have to deal with that. Let's do a little vector proof, okay? Okay, so ABC is an isosceles triangle. With AC equals BC. That's the beginning. This isn't the proof yet, this is just a setting up. And M is the midpoint of AB. Proves that angle AMC is a right angle. All right. So in the land before we learned about vectors, and probably most of the time, you would use some sort of similar triangle sort of argument to prove this. But we know about vectors, so we're going to attempt to do it with vectors. So we do know that every point on this line can be made as A plus some amount of the distance from A to B. And we know that the length of this vector from A to C is the same as the length of this vector from B to C. And various things like that. Our goal is to show that this line is perpendicular to this line. We'd like for this to be a right angle here. And so if those lines are perpendicular, the dot product of any vector on AB will be the same as with any vector on B, on MC should be 0. So that's my plan. I'm going to find some vectors. Okay, not sure how I'm going to do it at all at this point. But I do know some things, that M is A plus a half of the vector from A to B, because it's the midpoint. The vector from A to B gets you all the way from A to B, and if I went halfway, that would be the midpoint. You okay with that? Okay. That's how I think of it. It's also okay to say that the vector AM is half of the vector from A to B. That's an alternative way of saying the same thing. Like this arrow is half of this journey. I don't know if which of them is helpful at the moment. I'm just thinking about stuff. These are thinking at the moment. Okay, I know that the length of the vector AC is the same as the length of the vector BC, because I was told that. And the other things I know is that journeys can be added together if they're done head to tail. I know that AM plus MC is the same as AC. And similarly, I know that AB plus BC is also AC. Don't know if any of this is helpful yet, but. And there's lots of other little triangles like that I could make. Like I know that MB plus BC is MC, and all of this stuff. There's arrows I can make joining up in lots of different directions. Okay, so what I would like to do is I would like to prove that AB or possibly AM dot with MC is 0, because that would make a right angle here. So I want to show that AM dot with MC is 0. That's what I want. Okay. Okay. I'm just going to give it a go. AM, so that's all my thinking. AM dot with MC somehow have to show this is 0, right? So if I could build this out of stuff that would cancel out, that'd be good. So AM is the same as, I do know that AM is AC plus CM plus M, yeah. So this is AC plus CM. Okay. And CM is minus MC because they're in opposite directions. CM goes this way and MC goes that way. So they're in complete opposites of each other. So AC minus CM. Sorry, MC, sorry. Okay. So we have AC dot MC minus MC dot MC. Is that at all helpful? Possibly not. All right. I've just transferred this angle into the other angle over here. AC dot MC is this angle here. I haven't used the factor isosceles yet, have I? I hate doing these proofs. What'd be really nice is if I could have both sort of AC and BC in there because they're the same length, and that might be useful. So maybe I should make MC out of BC and MB. So MC is MB plus BC. Oh, I think I might see where I'm going and why that I need to start again. Because if I'm going to remove that MC, I should be removing this one as well. All right. Just a second. Okay, so AM is half of AB. So I reckon I'm actually going to just go AB dot MC instead of AM, because that would also make them perpendicular. It doesn't really matter how long this vector is, it only matters what direction it's going in. So AB is AC plus CB. And MC is MB plus BC. Yep. Yes. Okay. And just to make it clear so that everything's good, we've got AC and CB is minus BC. So I'll just do this so that they match. And MB is half of AB, which I reckon is going to be helpful. Could be wrong. Maybe not, I'll just leave it at that. So when I do this dot product, I've got AC dot with MB, that's those two. And then I've got AC dot with BC, that's those two. And then I've got BC dot with MB, that's those two, minus BC dot with BC. Damn it. Still not there, am I? This is the length of BC here, squared. So I could possibly replace that with the length of AC squared because I know they're equal. One more try, just a second. AB dot with MC is AB dot with, now MC is MB plus BC. And MB is half of AB, right? This vector is half of that vector. And so what I've got is half of AB dot AB plus a half of AB dot BC. But AB dot MC is also equal to AB dot MA plus AC, coming around the other way. So we went around this way and now we're going around this way. And that's AB dot MA. Now just a second before we do that, MA is going this way, so that's minus a half of AB. So this is AB dot, so minus a half of AB dot AB plus AB dot AC. Aha, I've got it. So AB dot B, this is an isosceles triangle, so these two angles are the same. So AB dot BC is involved with is a multiple of the cos of the angle at B, and AB dot AC is cos of the angle at A. Yeah, well, approximately with lengths and stuff. And so these two have to be, these two, that's not a half, sorry. These two are the same, which means these two are the same. Yeah, almost there. I'm nearly there. I'm doing so well. So 2 lots of AB times dot MC is going to be these 2 things added together. Yes, 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 yes. I'm nearly there. So now I've got 2 ways of doing AB.MC, right? This way and this way. If I add them together, then I'm going to have 2. I can't see it all on the same screen. 2 lots of AB.MC is this plus this, which is 0. Okay. Does this help me at all? Probably not. I may give up at this point. It's easier to do with similar triangles, but I don't actually, the vector proofs, I still haven't got good strategies for just coming up with the thing that works. I thought I was onto a winner there, because if I could make this, but then I'd need to know that those things were orthogonal, and that's just the same thing in the end, isn't it? So AC plus BC that's all right. Oh, it's worth a try. I'm going to annoy myself now. I know it's true, right? Because you're cutting it in half and it's totally a right angle. But nah, it should have all worked with my dot product calculations, but at least you can see some of the rules of how dot products work, and switching between one form of a vector and another. They're all moves that you make in these proofs, but I still haven't got good strategy to just get there. And so I just live in hope that they don't have one. And if they do, I just flail around and hope that they'll find something useful in there. And writing down, I want to show that the dot product of these things is 0 is a good place to start, because at least they know what you're aiming for. And you've proved to them you know useful things about vectors. So writing all this stuff down at the beginning at least shows that you know how vectors relate to diagrams like this. Yeah. I'm just staring at it, thinking about what I might try instead. That move of doing it 2 ways and like adding them is one of the things, because if you know that 2 of it is 0, then it has to be 0. And that's why I was hoping I saw, oh, you know, these are, one of them's minus and the other one's plus. That's so cool. They would cancel out, but that would require these to cancel out too. Which means that this vector, whatever it is perpendicular to that one as well, which really doesn't help very much. All right. I haven't really used the fact that those 2 lengths are equal, have I? I have tried to use the fact that those 2 angles were equal over here. Like I noticed that these 2 should be, they should be minus each other. So AB and BC, AB is this way and BC is this way, because this is ABC here, which means that AB and BC, when I put them head to tail, when I put them tail to tail, are this way, like, because that's how you do angles, you have to put them from tail to tail. Just a second. AB and, am I doing what? Oh, BC is this way. Damn it. Sorry, that's BC there. So when I put them head to tail, it's this angle here that I'm interested in, which is this angle here. Right. Okay. Better picture. ABC. If I put AB there and BC there, it's this angle I'm interested in, right? So AB dot BC is related to this angle, but AB dot AC, those two vectors are here, which is this angle here. And this angle is the same as this angle, which means that this angle is 180 degrees minus that angle, which means the cosine of those, one of them is minus the other, because that's how cosine works. And so this is minus that. So yeah, I don't really want to go into the causes and the sines of it, but that would be a way of fixing my proof and saying, well, the angle between this is 180 degrees minus the angle between this. So the cosines are negatives of each other. Yeah. Yeah. AB dot AC. No. Yeah. Wait. Ah, I think I have it. So we're back here. Yes. So AB is the same as AC plus CB. And MC is MB plus BC. I know this is what I was trying to do before, but just bear with me. That's AC minus BC. With a half of AB along the way. Nope. I'm just going to run with this proof and continue from where I was. I had this thing before, AB dot B, MC is AB dot MC plus MB plus BC, and that's half of AB, and I ended up here. But AB dot BC is AC plus BC dot BC. Because CB. Because to get from A to B is to go round this way. From AC to CB is the same as go from A to B. There's all journeys. And so, but CB is minus BC, so I'm going to do that too. Okay, so I've got half of AB dot AB plus AC dot BC minus BC dot BC. That's that bit. But the other half, so this was AB dot MC, but AB dot MC is also, whoops, according to this one, minus a half of AB dot AB plus AC plus BC plus CB dot AC is minus a half of AB dot AB plus AC dot AC. Technically, that's a minus BC, right? Okay. Yes, we have it. So just one more move. This is the length of AB squared. That's what you get when you dot a vector with itself, the square of its length. And this is AC dot BC. And this is the length of BC squared. And this is minus a half of the length of AB squared, And this is the length of AC squared. And this is minus AC dot BC. So the length of BC squared is the same as the length of AC squared because it is an isosceles triangle with those two lengths being equal. So this is the same as minus a half of AB squared plus the length of BC squared minus AC dot BC. And now if I add them together, 2 lots of AB dot MC is 0, 0, 0. Therefore, AB dot MC is 0. I got there. Probably not the most efficient way of doing it, but at least I got there. And I think the key with this one was the only information what I realized was the only information that I had to use somewhere was that AC is BC, which means I needed to write everything in terms of AC and BC. Yeah. Because I had to use the fact that they are equal. So if I wrote everything in terms of them, then I had a chance. Yeah. Rightio. That was horrible flailing. All right. So you talked about normals, and I haven't mentioned them yet. And normals are a squarely 3D thing. And they are referring to planes. And so I've talked about lines, and then I talked about vectors generally. And vectors in many ways are sort of about lines, really, because they point in a direction and that direction defines a line. But remember that vectors are also points if you need them to be like coordinates. Sets of coordinates are also points. And in 3D, there's not just lines, there's also planes. You know, just like my piece of paper is a plane. And planes are like lines, they're just two-dimensional. They're still flat the way that lines are. And so planes as well have Cartesian forms and vector forms. So, pardon me, a plane has 2 directions, not just one. I mean, there's, you know, infinitely many directions if you face in all different directions, but 2 directions are enough to tell you where a plane is. So there's enough information in a starting point and 2 directions to tell you where every point on the plane is. So they don't talk about the vector form of a plane in Maths 1M lecture material, but it is still there. So the vector, this is planes. The vector form would be a point plus t times a direction plus s times a different direction. So this would be a line with just one of them. If you have 2 different directions, it's plane. And the idea being that to get to every point on the plane, I'll go some amount of this direction and then some amount of this direction, that will give me a point on the plane. Or I'll go some amount of this direction, possibly the other way, and then some amount of this, that'll give me a different point on the plane. And so this S and T, you need 2 different letters because they're allowed to be different numbers. Yeah, that's the vector form of a plane. It tells you base point, 2 different directions, and you go one direction and then the other direction. That's like a coordinate system, like you would read a map. So that's the vector form of a plane, which is lovely. It doesn't really come up in Maths 1B very much, but Maths 1M very much, but it's nice to know that it's there. And that's why I know it's 2-dimensional, because I require 2 numbers to tell me where I am on the plane. Because that's what dimension means. So dimension is a way of, the number of numbers that describes it is the dimension that the thing is. So, you know, in a physical sense, a plane is two-dimensional because I need two numbers to tell me where I am. Whereas a line, you only need one number to tell you where you are, and so that's a one-dimensional object. Which is why curves are one-dimensional objects as well, because you only need one number to tell you where you are. Okay. In 3D, you only need one equation to tell you where a plane is. To not where a plane is, but this is the vector form, but there should be a Cartesian form as well. And the Cartesian form will look like this. AX plus BY plus CZ is D. It'll look something like that. That's the traditional version of a plane equation, but it doesn't really matter how it's arranged. You don't have to have all three of X, Y, and Z because these letter numbers here are allowed to be 0. And you're allowed to have like X equals Y minus Z. That's okay as well. It doesn't matter what order it's in, but as long as you can rearrange it to look like this, then it's a perfectly good Cartesian form of a plane. And lines have equations like that too, down in 2D. So the idea is that an equation that would normally be a line in 2 dimensions, when you're in 3 dimensions, it represents a plane. And you actually need 2 equations in 3D to make a line, because that's 2 planes meeting in a line in the middle. Yeah. So there's a magic trick with planes, which is very cool. So I know that when you dot product vectors, you get the 0 vector. Not the 0 vector, don't get a vector at all when you dot product vectors. When you dot product vectors, you get the number 0 if they're orthogonal. So it turns out that this point, so if you've got, just as an example, a plane with Cartesian equation this, something like that, and if you take the coefficients of X, Y, and Z and create a vector out of those, like that, then you are guaranteed that this vector as an arrow is orthogonal to any vector you could draw connecting 2 points in the plane. Just magic trick. And that idea of a vector being orthogonal to every vector that lives in the plane is called being the normal vector. And so i.e., it's the normal vector. So with a plane like this, it is possible for a vector to be perpendicular to some of the vectors in the plane, but for it to be perpendicular to all the vectors in the plane, it has to be perpendicular to the whole plane. That, as opposed to that. And that's a normal vector. And there are lots of normal vectors, but it turns out they are all multiples of this vector. And so, and there are good reasons why it works out this way, because if I see this as a vector, if I see this equation 3x plus 5y minus z equals 7, I can go, well, that's the same as the vector 3, 5 minus 1 dot with the vector x, y, z, and it comes out to the answer 7. So again, it's a Cartesian form. It tells you how to check if a point is on the plane, and a point is on the plane if it satisfies this equation. If you sub the coordinates in and it comes out to the answer 7, it's on the plane. If you sub them in and it comes out to something other than 7, it's not on the plane. But I can rewrite that as a dot product between 2 vectors, which is kind of cool. And so basically, if you treat all your vectors, all your points as the plane as the coordinates of vectors and do the dot product, the answer will be 7 every time if you dot it with this vector. It's really cool. So that means if you pick 2 points that are in the plane, 1, 1, 1, and 2, 2, 2, right, so x2, y2, z2. So this is 2 points that are in the plane. To create the vector between them, you'd subtract them, right? So if I go this minus this, I get 3, 5, minus 1. Actually, even better. So this is a point P1. This is going to be the point P2. So I've got the 3, 5, and this vector is going to be called n. That's what I'm going to call it. So now what I have is that n times any point on the plane comes out to 7. And n dot with any other point on the plane also comes out to 7. Watch what happens when I subtract these two equations. I've got n dot p1 minus n dot p2 will come out to 0. So this minus this. This is number 1, number 2, 1 minus 2. And I can factorize dot product p1 minus p2. That's the normal vector. This is a vector in the plane because it's the journey from P2 to P1. So what this is proving, it's not a very good proof, and I'm sorry, but what this proves is that this vector I made from the coordinates has to be perpendicular to any vector in the plane. Anything that connects 2 points in the plane, the dot product will be 0, it's perpendicular to everything. It's really cool. So because of that truth, the way to find the equation of a plane, and by that I mean the Cartesian equation of a plane, is to first find the normal vector. And so that means that whatever information about the plane you have to use it to find any vector that's perpendicular to all the vectors in the plane. That's what you need. And there is an operation you can do on vectors that will produce an answer that is perpendicular to both of the inputs. And it's called the cross product. So when you do the cross product of two vectors, I mean, you're supposed to put them next to each other like that. The cross product of two vectors is a new vector. The dot product of two vectors is a number. The cross product of two vectors is a new vector. And the cross product wasn't invented for this purpose. It just turned out this way that it actually happened. Yep. And it's a new vector, and it happens to be orthogonal to both the original vectors. So when the cross product was first designed back in like the 1870s, maybe the 1890s. Anyway, so Lewis Carroll, who wrote Alice in Wonderland, vector geometry was really new at the time, and yeah, it was new at the time when Alice in Wonderland was written, which is in 1865. But then in the intervening few years until 1900 or so, they turned that geometry into the cross product and the dot product. So yeah, but it wasn't invented to do this trick of being perpendicular to the two original vectors. It just turned out that way, which is just really cool that it turned out that way. So this cross product, there's a way of calculating it, and it involves, some people do it with a determinant of a matrix. I don't know if you've done it that way. Do you do matrix stuff in? No, doesn't matter. Have you calculated the cross product before?
Yeah.
So what you have to do is, I like to line them up on top of each other. And it'll be a different answer if you switch the order. And so it's really important, actually, for the purposes of finding normals for planes, it doesn't matter. But if you switch them in the opposite order, it'll be the same answer, but minus. So it takes me a while to get this right. It's going to be 3 coordinates. And the first coordinate is going to be made by crossing those two out and doing this. So 3 times 8 minus 2 times 5. That goes in the first coordinate. The second coordinate is going to be made by crossing the middle two out, and it's going to be 1 times 8 minus 7 times 5, only it's going to be minus that answer. Because the cross I'm trying to draw actually goes over the edge. So the cross I really want to draw is actually this one. It wraps around like a donut. And over here, there's a 1 and a 7 as well. If you go off this end, you come in this end, basically. So the cross I really want to draw is 5 times 7 minus 1 times 8 there. And then I'll cross this one out, and the other two is 1 times minus 2 minus 7 times 3. And that is the cross product. Yay. So whatever that works out to be is the answer. What, 24 plus 10, so that's 34. 35 minus 8 would be 27. And minus 2 minus 21 is minus 23. So you'll notice that when you do the cross product, you tend to get the numbers being bigger. And that's because in the same way as the dot product gets bigger if the dot product between two vectors is bigger if the vectors are longer. And it's the same for the cross product. Long vectors tend to produce longer cross products. In the same way as big numbers, when you multiply them, produce even bigger numbers. It's the same idea. And there's this rule that says that the length of the cross product is the same as the two lengths multiplied together and then times the sine of the angle between them. Yeah. That's the rule. So that basically the length of the answer is going to be bigger if the length of u is bigger. It's going to be bigger if the length of v is bigger, and it's going to be bigger if they're closer to pointing in the same direction. No. If they're orthogonal, they'll be bigger. Because sine gets bigger as the angle gets closer to 90 degrees. So the closer to right angles the two vectors are, the longer the cross product's going to be. For the purposes of trying to find a normal vector, it makes not the slightest difference how long that cross product is. It just matters what direction it points in. But you'll just notice that it tends to have bigger numbers than the original had because you're multiplying all this stuff together. And that's cross products, really. So if I wanted to find a vector that was perpendicular to two other vectors, then I could use the cross product to do it. And what that means is if I find two vectors in the plane that are not pointing in the same direction, the cross product of them will be perpendicular to both, and it will therefore be perpendicular to all the vectors in the plane. You only need to be perpendicular to two different vectors in the plane for it to be perpendicular to everything in the plane, which is really cool. Of course, if someone tells you the normal vector to begin with, then you can just write down the equation. So let me just talk about this. I'm going to do some examples. Find the equation of the plane. That's my short version of equation. It's just EQ and then N. Find the equation of the plane through the point 1, 5, minus 7 and normal to 6, 1, 0. So, two pieces of information we have to hold on to about the Cartesian form of a plane. All Cartesian forms are designed to decide whether a point is on the plane or not, or on the whatever the object is. So I know that when I find the equation, if I sub the point 1, 5, minus 7 into it, then it will work. I also know that when I do the normal vector, then those are the coefficients of the plane. So I know that the equation is 6x plus 1y plus 0z equals some number, which I don't know what that is yet. So I've got 6x plus y is some number, and I don't know what that number is. but it's definitely going to look like that. Absolutely certain, because that's how normal vectors work. The coordinates of the normal vector become the coefficients in the equation. All I need to do now to finish off the equation is figure out what D is. But the other piece of information I know is that if this really is the Cartesian equation of the plane, then every point that is on this plane will satisfy the equation. Because that's what Cartesian equations are for. You sub it in, and if it works, it's on the plane, and if it doesn't work, it's not on the plane. So I know that 1, 5, minus 7 satisfies the equation because it's on the plane. And so therefore 6 times 1 plus 5, and there is no z, so in the equation that's fine, must be d, and so therefore the d is 11. And so the equation is 6x plus y equals 11. How do you feel? This is not the way that some of the examples in the course work. So there's an alternative way of producing this same information, and I just want to show you that as well. But this is how I think about it. And this is fine. As long as you put all the words in, it'll be okay. The other way to say it is that, you know, let x, y, z be a point on the plane. And then you know that every vector in the plane is perpendicular to the normal vector. And so therefore this vector, damn it, the vector x, y, z minus 1, 5, negative 7 is therefore in the plane, because this is a point on the plane, 1, 5, 7 is a point on the plane, so this vector should be in the plane because it connects 2 points on the plane. Is in the plane and so orthogonal to the normal vector. And so an equation for the plane is x, y, z minus 1, 5, negative 7 dot with 6, 1, 0 is 0. That vector dot with the normal vector is 0. And that can allow you to find the equation of the plane as well. Expand this out and you'll get the answer. So you'll get x, y, z dot with 6, 1, 0 minus 1, 5, minus 7 dot with 6, 1, 0 is 0. 6x plus y with no z's minus whatever this answer works out to be, which is 11, is 0. Your lecturer doesn't write it this way either. They write it as x minus 1, y minus 5, z plus 7 dot with 6, 1, 0 equals 0, which is the same thing. But I just like this version. I prefer this version. It makes sense to me. But all the calculations are actually the same. So this dot product here is the same as 1 times 6 plus 5 times 1 plus minus 7 times 0. It's the same thing as subbing it into the equation. So it's all the same thing. You pick whichever makes the most sense to you. If you don't already have the normal vector, you're going to have to create it. And so I'm going to stop in a minute. A plane through 1, 1, 1, 0, 1, 3, and minus 1, 2, 7. You only need 3 points to make a plane. I'm just going to check that these 3 points are actually in a plane and not in a line. Like if they're all in a straight line, there's infinitely many planes through a line. Because you can put a line here and then spin the plane around the line, and there's lots of planes. So if they were all on a line, then the journey from this one to this one would be a multiple of the journey from this one to this one. So the journey from this to this is minus, well, the journey from here to here has a 1 in the first coordinate, and the journey from so this journey is 1, 0, minus 2. That's that journey. And this journey is 1, minus 1, minus 6, and they are not multiples of each other. And so this is not just a line. There is a plane through, there is one plane through those 3 points. So, okay. Okay, so just in case you're wondering, if someone asks, are these 3 points collinear, meaning they're on a straight line, then that's how to do it. Find the journey from one to another, and then find a journey between, basically you pick one of them and find the journey from the other points to it, or the other way around. And if those two things are multiples of each other, then it's the same direction to get from that point to the other two, so they're all in a line together, which is really cool. I like that. So they really are a plane. So to make a plane, I need a point on it, and I need a normal vector. And so I'm going to need to create a normal vector, which is cool because I've already done some 2 vectors that are in the plane. I'm just going to draw it as a diagram. Here's 1, 1, 1. I've actually done these arrows, which is fine. So this arrow here was 1, 0, minus 2, and this arrow here was minus 1, 2, 7. It doesn't matter which way around you subtract them, you just need 2 vectors. So I've created 2 vectors by subtracting, by figuring out the journey between one point and the other 2 points. And these 2 vectors are definitely inside the plane. The normal vector has to be perpendicular to both of them. And so I'm going to need, therefore it's the cross product. How are you feeling about that? So I'm going to say the cross product of 1, 0, 2, minus 2 cross with minus 1, 2, 7. No, damn it, that's the wrong vector. It's this vector, 1, minus 1, 6. Minus 6. Sorry about that. 1, minus 1, minus 6. And that's going to be 0 minus 1 times minus 2, and then it's going to be minus 2 times 1 minus 6 times 1, and then the last one is minus 1 minus 0. Okay, so I've got minus 2. 2 plus 6 is 4. And that's minus 1. So that's my cross product. And so this is a normal vector. So I know that the equation is minus 2x plus 4y minus z equals some constant. But I don't know what the constant is yet. But I do know that no matter which point I sub into this, it will give me the same answer for D, because they all give the same answer for D, because that's the point of this equation. And so I know that 1, 1, 1 is on the plane. So minus 2 times 1 plus 4 times 1 minus 1 should be D. So D is minus 2 plus 4 minus 1, which is 1. Nice. And so therefore the equation is minus 2x plus 4y minus z equals 1. Yay. So just to check it's really working, the other points should satisfy it as well. So 0, 1, 3, let's just check. The point 0, 1, 3 should satisfy. So minus 2 times 0 plus 4 times 1 minus 3 is indeed 1. Okay, it's working. And the other point should work as well, the minus 1, 2, 7. So let's just check. Minus 1, 2, 7. So we've got minus 2 times minus 1 plus 4 times 2 minus 7. So we've got, I'm I think I've done something wrong then. No, it's okay. It does work. Okay. So this is -2. This is -7. So that's -9. I've got 8 minus 9. That's -1. Damn it. No, nope, it's all right. -2 times -1 is +2. 2 plus 8 is 10. 10 minus, for the sake of failed David. All right, I've done something wrong. Oh, it was a triple negative though, because it was this minus this times this. Ah, this is a 2. So I've done all my calculations wrong anyway. All right, that's why it's not working, because I did this journey as 1 minus minus 1, and I did that as 1. But it's actually a 2. Yeah. So my journey is wrong. Therefore, I shall make this a 0, and then it'll be fine. Change the original question. I wish you could do that in your exam. And then 8 minus 7 is 1. Tick. Okay. But that's what I did wrong. And unfortunately, it was right back at the beginning. So I would have to go back and change this, and that would change the normal vector, and it would change the number. Right. Okay. At least I know what the problem was now. But I'm glad I checked, right? Glad I checked. Right. That's a good moral to end on. Don't forget, you can always sub in the other points to check. But any system by which you can find the vector that's perpendicular to both is fine. You don't actually have to use a dot product to do that. If you happen to stare at it and just notice something that you realize is perpendicular to both, then that's fine too. Yeah. So the only other situation is when you're given if you're given a line and a point, that can make a plane as well. And so you have a point and a line, then your point is a point, and your line also has a point and an arrow, because you write it in vector form. And then these 2 points can give you the other vector, and then from those 2 vectors, you can make the normal vector. Yeah. So as long as you can create 2 vectors in the plane, you can do a cross product to find them. Yeah. To find the normal vector. I'm going to stop there.